Okay, this lesson is on deviation. Deviation is a numerical way to measure what we call precision of our lab data. How precise our data is tells us how relatively close our values in sample trials are. So again, I'm referring to our example sheet given out in class using the same 4 example trials that we used to calculate error in the last lesson. And looking over these values, we see that they're all fairly close to one another. So if they were 4 trials of what should have been the same outcome, we could probably conclude they have low deviation. They do not deviate much from each other, but just how much do they have in the terms of a value is what we use the calculations of absolute deviation and, more importantly, relative deviation for. And again, this tells us, using the term, how precise our values are, how close they are to one another. This has nothing to do with the final accepted value as error dealt with. So first of all, let's look at the variables involved in our formula. D sub A is absolute deviation. And through this tiny formula, O again means the observed trial, so any of these numbers down here, for example. M means the mean, or in other words, average of all our trials. In this case, we have 4 trials, so we'll take the average of those 4. And this M over here is the same exact value as this one. Everywhere see a M, we use a mean, which we will calculate in a moment. The dA average will be the average of every individual absolute deviation, which we'll have to carry out in a moment. The process should not be difficult, but depending on how many trials we have, it can be lengthy, so just follow with me here. Alright, we are now on number 3 of our example sheet. So one little thing at a time here. Number 3 says, find the absolute deviation for trial 1. So we'll say dA sub 1. However, before doing any of this, we really need to find what the mean of all our trials are. So we do a quick average of all these numbers, which means summing them up, and in this case dividing by 4, obviously. And our mean of all these numbers, which I'll put underneath, I'm not going to show the work for this because it's simple. Our mean is equal to 23.0, if I round it off to 1 decimal place. And that will be used anywhere in the above formulas that we see of an M. Now, the absolute deviation for just trial 1 is the observed value in trial 1, 22.4, minus the 23 we found for the mean, and taking its absolute value, 22.4 minus 23.0. And that will be a value of 0.6. Alright, moving on to number 4. It now asks to find the dA average, as it's referring to on your sheet. If you notice, that is the numerator of the formula above for relative deviation. So this is necessary to find this value, which I signify as this on the sheet, to find the relative deviation of all your data. Now this is where the lengthy part comes in. It's easy, however, we need to find the absolute deviation for every trial. In number 3, we already are asked to find the absolute deviation for trial 1, so we'll not redo that one. It's 0.6 as listed above. dA2 is going to be done the same way, but use the specific observed value for trial 2, which is 23.8. Minus the same mean. That mean will not change. Always use that value. So dA2 is going to be equal to 0.8. Now I think we got the hang of it, so to save a little time here, I'm just going to tell you the value for dA3. Again, all we would do is plug in 21.6 for the observed and subtracting like we did up here, and the absolute deviation for trial 3 is 1.4. And for trial 4, doing it similarly with the 24.3, the absolute deviation for this will come out 1.3. Now, what we have is the average, or need the average of every absolute deviation. And again, you can see where this kind of could get lengthy if we had many more trials than just 4. Lengthy but not hard. So all the numbers I just underlined, we need to take the average from. And that will be this dA average, which we could write in now. So summing up those 4, dividing by 4 in this case, will give me an average deviation, rounded to 1 decimal place, of 1.0. Okay, and finally, number 5 on the sheet tells us to find the most important value that we would typically be asked for in a lab with a lot of data where we're trying to find the precision of our measurements using deviation, would be to find the relative deviation. As on the prior page, the formula says relative deviation equals dA average. We found that out already. That is 1.0 over the mean, which we found out early to calculate all those absolute deviations, and that number was 23.0. We divide times by 100 to get it in the form of a percentage. And in this case, rounded to 1 decimal place, we get a relative, or in other words, percent deviation of 4.3%. And that sounds pretty good. Obviously, the higher the number that is, the more our trials deviated from one another for the same scenario. Therefore, if we get a fairly high number here, we probably want to go back and look why, if those numbers are supposed to be practically identical. So relative deviation might be lengthy, but hopefully after watching this, you realize that it is not very difficult. And in most cases, you'll be asked to do everything all in one step. To simplify the process, I broke it down into some individual steps in numbers 3, 4, and 5.